Okay, so for section 12.2, we're going to stretch it over 2 days, but the topics are really pretty darn similar to each other. The first day, which is today, we're going to look at homogeneity, which essentially means for 2 different populations, are the category proportions the same? For instance, let's say we're trying to see if men are going to be more manly when they go to the store and not use a shopping basket. They're going to try to carry everything. Doesn't matter that you're buying $100 worth of groceries. You want to carry it because you can. I'll push around a big basket. Well, so one thing you can do is test, look at males, look at females, and see are the proportions that get a basket, like a buggy, versus just a basket you carry in your hand versus nothing. Are those proportions the same for both male and female? If they are, then your data is homogeneous. And then tomorrow we're going to look at independence. And I think independence is pretty self-explanatory. So using that example, it's whether or not you get something to carry your groceries in, is that independent of gender? So they're really, like I said, they're pretty much the same test, same process. Only thing that you can tell them apart is based on your hypotheses. So let's jump in and kind of set the stage. So both days we're going to be using a 2-way table. Friday we looked at a 1-way table where it was just one population, however many categories we were going to group them into and go that route. Now we're going to have multiple populations and multiple categories. One such data set was that we've kind of been using throughout the semester sporadically. It's the student data set, and they gave a sample of 79 students taking elementary statistics. Now, in that data set, 2 of the variables were vision correction and then gender. So male and female. And then for vision correction, did they wear contacts, glasses, or nothing? They don't need vision correction. So this is an example of a 2-way table. Or when we did probability, we called this a contingency table. Now the number of cells that this table has is just however many white boxes essentially that you see up here. Where did my pen go? There it is. So we see six boxes right there. So there are 6 cells with observed counts. But on these tables, whether we're doing homogeneity or independence, we're going to need these cell counts, or the marginal counts. So let's get our marginal totals. So for the row, you just add them all up. 5 plus 9 plus 11 will give you 25. Then we do the same for males. 5 plus 22 plus 27 will give you 54. Then you go through and you do the columns. So for contacts, 5 plus 5 is 10. 9 plus 22 gives you 31. And then 11 plus 27 is 38. And then this box right here we call the grand total. So it should be the sum of the rows and the sum of the columns. No matter which way you add them up, you should get, in our case, it'll be 79. So the sum of the column marginal totals or the row marginal totals we call the grand total. It's also the total number of observations that you've done. So typically with a two-way table, we use it to test homogeneity. The rows indicate the populations and the columns indicate the different categories, or vice versa. So we could say columns would be the populations, rows are the categories. However you set it up, you got the categories going one way, populations going the other. For a test of homogeneity, the central question is whether the category proportions are the same for all populations. So we want to see, are they the same for all populations? Are men really as manly as they think they are? I don't know. I can't say too much. Doesn't matter if I'm going in for, if I'm going to go in for even 5 items, I'm usually getting a bogey. Now, bringing it in from the car, yes, I agree with that. Yeah. Yeah. I tried that once unloading luggage one time, and it didn't really work out in my favor. Because I had a portable DVD player and didn't put it in my case and set it on top. Well, what was the first thing to fall? The DVD player. And it fell on the concrete garage floor. So, yeah, there was the end of that. Yeah. I actually saw a trick. You get a broom. You just put the bags all along the broom and you just carry the broom. Yeah. Okay, so when the row indicates the population, the expected count for a cell is simply the overall proportion that have the category times the number in the population. Now, if you're like me, when you first read that, or I just first said it, you may be thinking, okay, yeah, is this even in English right now? I didn't understand what it was saying until they illustrated it like we're going to do on the top of page 7. So if we look at contacts, for instance, the overall proportion of students who use contacts would be 10 out of 79. Then we have 50. Yes, well. Yeah, okay. And then we have 54 total male students. Make sure we're writing all these proportions down. They're on the page 7. So the expected number of males that would wear contacts would be 10 over 79 times 54, which gives you 6.83. Now, on this one, that's one way you could look at it and multiply it. But a more intuitive way may be to, instead of separating it like this, it may be to say, let's do 10 times 54. So the marginal totals divided by the grand total. So we did 10 times 54 divided by the grand. That may be a little bit more intuitive than writing it in this manner that they have it on the slide here. And that's actually how we get expected cell count. Will, on that, are you needing that blank on the bottom of page 6? Yeah, the last the very last bullet point? No, second to last. Same. The word same. Okay, so the expected values in each cell represent what would be expected if there was no difference between the groups under study. And we can find them like we just kind of got from that example. You do row times column totals divided by the grand total. Row times column divided by grand total. Okay, so let's look at our table here. We kind of already did this one, so what I'm going to do is I'm going to claim, where is my marker? I'm going to claim that cell, and then I want y'all to pick one of these other cells and claim it and calculate the expected count. So this one was that little illustration we did. We say you do 10 times 54 divided by the grand total. Now on your notes, there's actually 2 tables there. The first table is to write the calculation in. The second table is to write your answer. So like in the first table, you'd say 10 times 54 divided by 79. In the second table, you'd say that's 6.84. Which that's exactly what this is. 6.84. Okay, so does anyone want to claim one of their cells up here? Are y'all? You want to do the females with contacts? Okay, well, what I'm going to do is I'm going to write y'all's name in it, and then as we get to it, I'll call you. Will, which one would you like to do? No glasses. No glasses, okay. And Nate. Yes. Females with no glasses. Okay, those of y'all that are virtual, I need 2 of y'all to claim one of the remaining 2 cells. If you put your choice in chat. And while y'all are picking the remaining 2, we'll start filling in the ones that have been claimed. Yancey, I need you to tell us how you calculated it and then what you got. Okay, 10 times 25, divided by 79. 3.16. Okay. David claimed that one. Okay. Nate, would you like to do yours? Okay, how did you calculate it? Okay, so 38 times 25 over 79, and I got you 12.03. Okay, Will. 54 times 31 over 79. And I got you 21.19. Yep. Okay, and then David. Yep, and how did you calculate it, David? Bless you. $31 times 25 divided by 79. That's right. That gets us 9.81. Okay, and then Mia. That's right. And how did you calculate it? $38 times 54 divided by 79. Good. That would get you 25.97. Okay, so that's how we get expected counts for a two-way table. Questions on that? No? Okay, and that's the same for whether we're looking at homogeneity or independence. That's how you get two-way counts, or two-way expected counts. So now let's focus specifically on homogeneity. The null hypothesis is that the true category proportions are the same for all populations or treatments. True proportions are the same. Which means the alternative is that the true proportions are not the same for all populations. Now, the test statistic will look pretty familiar, or it should at least. It's the sum of the observed count minus the expected count squared divided by your expected count. So observed minus expected squared divided by expected. This is the same formula that we had for our test statistic as on Friday. Okay, there you go. Sorry about that. Okay, so for the expected counts, we already calculated them, but let's just kind of make it official when talking about the process. So the expected cell count is the row marginal total times the column marginal total divided by the grand total. So we already said the formula once, but we'll say it again. And then for the p-value, when the null is true, and all expected counts are at least 5, x squared has approximately a chi-square distribution where the degrees of freedom, the number of rows minus 1, times the number of columns minus 1. The p-value associated with the computed test statistic is the area to the right. So that's just like what we did on Friday. We're going to still use our chi-squared table on these tests. So the p-value is the area to the right of your test statistic. You get the part on the top of the next page, Will? Area to the right is what goes in that blank. Okay, and it wouldn't be a hypothesis test if we didn't have some assumptions. You gotta have assumptions, right? So the first assumption, the data has to be independently chosen random samples. Or the subjects have to be assigned at random to treatment groups. So it's gotta be a random sample. Same thing we've said pretty much all semester. Also, the sample sizes must be large. The way we're going to tell on this one is if all the expected counts are at least 5. If some of them are less than 5, then we're going to have to combine either rows or columns. So let me ask you this. The table that we just computed the expected counts on, would that one be good to start carrying the test out with? If you get also all our cell counts are at least 5? You expect the ones we calculated, all the expected counts are 5 or higher? We what? Well, no, it means like the expected counts. So the 9.81, the 21.19.
Oh, no, we got one. Oh, we got 5 for one.
One is less than 5, so we would have to combine them. That tells us we need to combine categories. And we're actually going to use that table tomorrow, and we'll have that same conclusion. We'll say, oh, no, we got to combine. Okay, so let's look at our first example. A study was conducted to determine if collegiate soccer players had an increased risk of concussions over other athletes or just other students that don't even play sports. So the two-way frequency table below displays the number of previous concussions for students in independently selected random samples of 91 soccer players, 96 non-soccer athletes, and 53 non-athletes. So this is also, yes, we're calling it a frequency table. You can call it a contingency table. Whatever. It's a two-way table. And this is univariate categorical data. The thing we're measuring is the number of concussions. number of concussions, and they're coming from 3 independent samples: soccer players, non-soccer players, and non-athletes. So let's answer this first question. If there were no difference between these three populations, how many soccer players would you expect to have no concussions? How can I get the expected count for this cell right here? What could I do? Anyone have an idea? 158 times 91 divided by 240. So if we did that, what would we get to 2 decimal places? $59.91, that's right. And we're dealing with soccer. We're dealing with soccer players here. So. Okay. So now let's state our hypotheses. So what would our null hypothesis be? Well, we could say that the proportions in each response category, which are response categories of the number of concussions, are the same for each of the 3 groups. So we expect the same proportion of soccer players to get 1 concussion as we would expect for non-athletes, for instance. The proportions in each category are the same for all 3 groups, which means our alternative is the exact opposite of that. They're not all the same. We're not saying which ones aren't the same. We're just saying not all of them are the same. Kind of like Fridays. We're like, one of these is not like the other. Which one doesn't belong? just a little side note, when I was going through this example, I was like, I don't see how soccer players could get more concussions than others. And then I started thinking, wait a minute, they're sliding around on the field, feet are flying and everything. Yeah, okay, I can see that. And they're not wearing many pads. Have you? Yeah. It's not like football where you're surrounded by pads. That's why I was like, oh, you're just running around kicking a ball. How can that give you a concussion? Yeah. Of course, heck, even in football with all the pads, you still get concussions. That's why you what?
You hit harder.
You hit harder. Yeah. Okay, so while this table is up here, let's try to figure out how many degrees of freedom we have. So when we compute degrees of freedom, we don't want to count our total row as a row in the data. So if we're looking at like how many rows does the data have in columns, you don't count the total row or column. That one's ignored. So how many rows would we have then? We got 3 rows. And so how many columns do we have? 4. So to get the degrees of freedom, you do rows minus 1, number of columns minus 1. So 3 minus 1 is 2. 4 minus 1 is 3. 2 times 3 is 6. So this data has 6 degrees of freedom. As it is. We're not saying it's a good set of data, but as it is, it's got 6 degrees of freedom. Now, do y'all want to know a shortcut to where y'all don't have to remember the formula? Cross out a row, cross out a column. How many cells are left? 6. So cross out a row, cross out a column, and then count how many cells are left. That would get you your degrees of freedom. And I've explained why we're calling them degrees of freedom, right? Have I explained that? Just in general this semester? I think so. You don't remember? Okay, so the reason we call them degrees of freedom is like, for instance, when I said cross out these right here, the 6 degrees of freedom mean that these 6 that are left can be anything they want to be. But for our test to be consistent, yes, these are free to be whatever, but for the test to be consistent, once you determine these 6, it locks these into place. These don't have any freedom to change. These 6 could, but once these 6 are set, it sets these. They have no freedom. Does that make sense? What's that? Yeah, it could be. Like, I mean, you could, if you pick 6 numbers here, once you set those 6, the others have to fall in order as is. So if I picked, let's say I wanted to pick that one, you know, I just went through and I picked 6 of them, however I wanted to pick them. Once I set these, then the remaining as it were, the remaining sets, they would be set. They would have to be set, and they couldn't change. So 6 have a freedom to change. The others are set. They have to be set in order for it to stay consistent. Okay, don't forget that. Okay, so we've calculated expected counts. I'm going to save us some time. Last period I had us all calculate these, but I'm going to save us some time and not make us calculate all the expected counts. So on the next table, on the top of page 9, let's write in the expected counts, which are the ones in parentheses here. And just to recap, to get this 59.9, we would have to do 158 times 91 divided by 240. Okay, so let's check our assumptions. We have our expected counts. Let's check our assumptions. I'm going to kind of do that. I really don't have much room unless that. Yeah, that's not going to go away. Okay, fine. Okay, so first assumption we've got to look at, are they random? Does the problem tell us anything about these being random? Let's see.
Yeah.
Yep, it says students and independently selected random samples. So yes, this is random and stated in problem. Okay, second thing we've got to check. Is this a large sample? Go back. You've been paying attention. I'm kind of unintentionally flashing the answer up there like crazy. So, is this a large sample? No. What's wrong with it? Some of these aren't above 5. I have one that's a 4.9, one that's a 3.3. So, what do y'all think then would be a good solution to fix this? Combine rows or combine columns? Combine columns. Yep. Since we have one in each column, we can combine these two together and say 2 or more concussions and go that route. So let's do that. Boom, we combined them. Now, let's look at our counts. So your combined table is down there kind of in the middle of page 9. Notice that our expected counts for the first 2 columns didn't change. That's because we didn't change those columns. They stayed the same. The only columns we altered were the last two. And even then, you may notice something. Well, for one thing, you may want to check your notes. I corrected this on the PowerPoint this weekend when I was going through these, but this number, check yours. I think yours says, what, 22 still? You make sure you change that to 37. There's a typo on the notes. And then now we have our new expected count for this last column. So now that we have a large sample, we do. So we're good to proceed, but being that we combine columns, that means we've changed our degrees of freedom now. So we have to get a new degree of freedom. I'm going to say that right here, new DF. How many rows do we have? 3, so 3 minus 1 times. How many columns do we have now? 3, but then when we take 1 out, we're left with 2. That's right. So it's going to be 2 times 2, which is 4. So we lost 2 degrees of freedom when we had to combine that column. Now we only have 4 degrees of freedom. Okay, well, I guess that's not going to let me not show the calculation. So the next step is to calculate the test statistic. So we just start at the first cell, and we say observed minus expected squared divided by the expected. Observed minus expected squared divided by expected. And we just keep going through each of these. I'm going to save y'all the hassle because y'all are going to have to do it on the homework. So I think y'all can punch buttons on the calculator to get that answer. Again, on your assignment, it's perfectly valid to write it like this. However, here's my little word of caution. As you're about to see on this example, once we work everything out, it'll say, okay, is that all we can say is this conclusion? And you're like, no. If we write everything out and we say, okay, so let's say I write out all 9 of these and I calculate this. So I didn't even do that in my notes. Let me reach back here and do it real quick. So 45 minus 59.9 squared divided by 59.9. Let's say I go through and I calculate all of these. 3.71, whatever that one is. Plus, plus, minus 8.2 squared divided by 8.2. 3.30. And I did that. I can actually go through and see which one of these contributed the most to this chi-squared statistic. And that'll tell you which one of these is not like the other. So, yes, the hypothesis test will tell you overall yes or no on whether they're the same. But then you can go through and see, okay, which one's the most different? Which one screwed everything up for us, possibly? You go that route. Okay, and then if we look in our table, so this p-value is kind of high, so I'm going to hide it for now. If we look at our table, we have 4 degrees of freedom. 20.6 is our test statistic. What would our table tell us the p-value would be? Let me get our table. Let me pull up our table and then we can, unless one of y'all already have it. Greater than 0.005?
Oh, yeah.
It'd be less than 0.005. So, let's see. There we go. There's our chi-squared values. Okay, so if we look here, how many degrees of freedom did we have? 4. Okay, so 4 degrees of freedom. If you notice, we're counting down up here. On top, we're counting down. So we're going to go less than 0.005 because at 0.0005, our critical value is 20. We're bigger than 20. So from the table, the best we can say for p-value, best we can say is that it's less than 0.0005. But we can use our calculator. If we use the calculator, and I'll come back to this screen in case you haven't gotten it written down. If we use the TI-84, that's what I'm going to demonstrate it on. You can go to second and bars, and then pick option 8 for chi-squared CDF. You can see mine's already in there because I did it last period. So 20.61 is the lower bound. Your test statistic is always your lower bound. Upper is just a big number. And then we have our degrees of freedom. Now, if you have to type it in on by hand, it would look like this. So this would come up, and then you would have to type this in. So lower, upper, degree of freedom. Hit enter. And it gives us that e to the -4, which means we've got to move our decimal place over 1, 2, 3, 4 times. So the true p-value is 0.005. 0.000378. That's what we get from the calculator. Regardless of whether we use the table or we use the calculator value, do they give us an alpha to test that? No. Even if, let's say I use the alpha of 0.01, one of our smaller alphas, right? What would I do with this hypothesis? What would my conclusion be? It's still smaller than 0.01, so we would reject it. Yeah. So since p-value is less than alpha, any reasonable alpha, we would reject the null hypothesis. There's strong evidence to suggest that the category proportions for the number of concussions is not the same for the three groups. And this is where I said we could dig a little bit deeper. So this isn't all. And we could say, yes, we're rejecting H0, which means they are different. But then we can look and dig a little bit deeper and see, okay, which one of these contributed the most to our chi-squared? And to do that, we would really need to see everything calculated out. That's why I was saying, yes, you can do first one plus ... last one. But if you're really wanting to see, okay, where's the difference at, that's not going to help you much. So as we're going to see on, I want to say it's the next example. It really would help when you have them all written out. Okay. So we can look to see about the which contributes the most. So they found that these three had the largest contributions to the chi-squared statistic. So soccer players with basically 1 and then 2 or more concussions, and then non-athletes had none. Those contributed the most. I think it's safe to say that soccer players, yeah, they do tend to get more concussions. Okay, next example. It's talking about some kind of drug trial for cancer patients. So this came from a clinical trial of a drug regime used in treating a type of cancer. I'm not sure exactly how you pronounce it. If I had to guess, it would be lymphocytic lymphoma. Yes. And a sample of 273 patients were randomly divided into 2 groups. So there's that word random. They were randomly divided into 2 groups. One group of patients received cytotoxin plus prednisone, which we're going to just call CP. The other received BCNE, whatever that stands for, plus prednisone, which we're calling BP. And the responses to the treatments were graded on a qualitative scale. So they summarized the data in this table. That table's on the top of page 10. And then it says set up and perform an appropriate hypothesis test at the 0.05 level of significance to see if they're the same. So first, we need to get our marginal totals. So for BP, if we add them all up, we get what? What's that? 138. That's all right. Oh, they did columns first. Okay, let's do columns first. So complete response, you add them up and you get 57. Next one's 110. 32. 74. And then the row where he said 138. Next one would be 135. That's right. Which means our grand total is 273. That's right. And that should be 273 because that's how many they tested. I hope we didn't have an extra one sneak in there and try to do the test. So once we do that, we have to check our assumptions. Make sure we don't need to combine anything. So they tell us the samples were chosen randomly. And I don't mean by they tell us that up on the screen. I mean in the problem. I think I underlined the word random. They said that they were randomly divided. And well, we got to check, are all expected counts greater than 5? So we've already done expected counts a couple of times. I'll go on and give those to y'all. Like I said, we've already done them a couple of times. So I've written the formulas down. I trust that y'all either know how to do it or you can ask me for help. So then we've got to look at these. For all the expected counts, at least 5. Definitely yes. Okay. So our assumptions are good. Let's look at our hypotheses. So what would be our null hypothesis? How could we say that? Yeah, that's kind of on the right track. We'd say that the true responses are the same for both treatments. We don't want to say they cured it because we don't know that they cured it, but the proportions are the same for both treatments. That's how we get homogeneity. They're the same. Proportions are the same. So we have our null. What would the alternative be? Now they're not the same. That's right. But these, like I told third period, these hypotheses for the next couple of days are going to be more of sentences than actual, like just writing stuff. They're going to be more sentences than anything. No, I don't want to say no numbers involved, but very few numbers involved in the hypotheses. So once we get our hypotheses, let's start talking about degrees of freedom. So in the data, y'all don't have, y'all have the table right above this. On PowerPoint, I'd have to go back a slide. But for degrees of freedom, how many rows do I have? 2. So let me kind of make note of that here. Degree of freedom. We know we're going to have to say 2 minus 1. How many columns do I have? 4. 4 minus 1 is 3. So I'm going to have 1 times 3, which gives me 3. I only have 3 degrees of freedom. Let's see. Did they give me an alpha level to test that? Yes. What was our alpha level? 0.05. So I know my degrees of freedom. I know my alpha. What do y'all think the next thing we should do is? Test statistic. Okay, so you can write the formula down or not. It's up to you. We observe minus expected squared divided by expected. Same process that we've done. So here's the calculation in all of its glory. Notice this one, they did not do the dot, dot, dot. They went through and they wrote each one of them out. And this is what I was talking about. This is one of the advantages. Because let's just say we're going to reject. We could go through now and see, okay, which one contributed the most? That one's pretty big. 0.0.0. That one's kind of big. So these two were our top contributors. Now, if you're writing this in your notes and you don't want to write all 8 of these, you can still do the first one plus dot, 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 plus the last one. But I just wanted to show you all the advantage of writing it all out. You can actually see what's going on and how your test statistic is being impacted. Now, if you're writing this paragraph down, I wouldn't exactly write it down. We've already calculated the degrees of freedom, so you don't need to even write anything above this line right here. You don't need to write these 2 rows down. And then this is kind of wordy down here. So let's look at p-values, because I don't like how they explained it here in this paragraph. So for the p-value, we calculated earlier that degrees of freedom were 3. So if you look at the table under 3 degrees of freedom, you would get that the p-value would have to be between 0.20 and 0.25. So this is all you get with the table. If you do it in the calculator, though, I know I'm kind of rushing it, but we're getting tight on time. With the calculator, you would get a p-value of 0.2042. And we know that alpha They gave us an alpha of 0.05. So even down here, you can ignore this. Since the p-value is greater than alpha, H naught is not rejected. So we fail to reject H naught, which means there's insufficient evidence to conclude that the response rates are different for the two treatments. Again, notice we're not saying that they're the same. We're just saying there's not enough to conclude that they're different. Okay, last example. We're going to try to beat the clock here. Got 9 minutes. I think we can do it. So, student, this is where our manly man deal at the supermarket came from earlier. Student decides to study shoppers at a local supermarket to see if males and females exhibited the same behavior with regards to the device used to carry items. He observed 57 shoppers. Presumably, we're going to say they were random. And obtained the results summarized in this table. Determine if the carrying device proportions are the same for both genders using a 0.05 level of significance. The first thing we got to do is get our marginal totals. Let's go and do the rows first. Sorry, the columns first. Right? Yeah. All right. So for the cart column, 9 plus 17 is 16. 21 plus 7? 5 plus 8. Then we go through and do the rows. 9 plus 21 plus 5. Yep. And then 7 plus 7 plus 8. If we combine those together, what do we get? 57. Which I have to laugh. I ask you all this, but then if you look right below, they're all printed there. So instead of having y'all calculate everything, I gave y'all the mini tab output. So from this output, notice a couple of things. First, these bottom numbers, the decimals right here, are your expected counts. And these are your expected counts. Down here where it says chi-square, this number is your test statistic. They calculated it for you. DF, well, what do you think DF stands for? Degrees of freedom, just like it always has. And then p-value, they calculated that for you. So just using this output, and we're going to get to the conclusion here in a second, but just using this output and the fact that they want us to test at an alpha of 0.05, what would we do to the null? Would we reject or fail to reject? Fail to reject. So let's write our hypotheses. The null is that the true proportions are the same. for both genders. Well, the alternative is that they are not the same for both genders. They told us that significance level was 0.05. That's what they wanted us to test at. And then, yes, there's our formula for the test statistic. It's great and all, but they did all that for us. So under test statistic, if you wanted to write anything under test statistic, what I would do is I'd write the formula, leaving out the word cell count. I mean, you don't have to write cell count unless you just really want to. This, and then say this is equal to 5.251, because they gave that to us. Okay, and then with that in mind, our p-value is 0.072. And we already said since alpha is 0.05, we would fail to reject. Which means there's insufficient evidence to support a claim that males and females are not the same in terms of what they use to carry the groceries. Which means, I guess, men are mainly men. They use a grocery cart. Either that or women kind of be like us and carry everything too. What's that? Okay, so that's it for today. Tomorrow we're going to look at testing for independence. And that'll be the last day of chapter 12. Chapter 12 is a really, really short chapter.